Hi there. This video is to talk about the common ion effect, what it is, and how it's going to affect our math. So here we go. These are factors that affect solubility. I'm really only covering two this segment of our big idea 6, and then we're going to go into more after we learn about acid-base. So number 1 is about the common ion effect, which is really Le Chatelier's principle. Taking a look at what it means. If one of the ions in a solution equilibrium is already dissolved in the solution, the equilibrium will shift to the left and the solubility of the salt will decrease. Okay, that's a lot of words. What it's really saying is, if you've got a saturated solution, so in other words, most of it is a solid, but some has dissolved, the maximum of stuff has dissolved inside the solution. It looks like this at equilibrium. If you happen to add more barium ions, then this side will be too heavy according to Le Chatelier's principle. The Q is no longer able to decay, so it has to shift to create more solid to reestablish equilibrium. That's a common ion effect. If you add a common ion like barium or sulfate, it's going to shift to produce more solid. It's a way to make more solid. So what we're going to do is cover this math question here, which I happen to have right here. Okay. We're going to do number 1, and then on a separate video I'm going to do number 2. That way you can watch whatever video you want to watch. Okay. So, calculate the molar solubility of CaF2 in 25 degrees Celsius in a solution that's 0.01 molar CaNO32. Okay. The first thing I can see is KSP. Whoops. Go in here. Okay. And it's talking about molar solubility of calcium fluoride. So what I'm going to do is, what it's telling me is the KSP of calcium fluoride is this 3.9 times 10 to the negative 11. So I'm going to write the equilibrium equation. So it makes calcium ions and fluorine ions. Happens to make 2 fluorine ions, which gives me a KSP value of calcium ions times concentration of fluorine ions squared. Okay, now what I can see is I've got something that's saturated, but then I've added a common ion. In fact, this calcium is my common ion. So this makes me think of an ice table. I've got equilibrium, and then suddenly I add some calcium nitrate or some sort of substance to it. So I'm going ice table on this. I don't have to worry about the solids, so I'm going to cross that out. At the beginning of time, I already have an equilibrium solution, so I really do have x and 2x of this. I could solve what that x and 2x is by plugging in the KSP, but that's not important right now. I'm going to do that at the end when I get my equilibrium. Because then what happened is I had a change. The change was I suddenly added this much stuff. That was my common ion added. Now the nitrate doesn't really matter, so what I'm really adding is this many calciums. Now we do need to be careful though, because it is a 1 calcium to 1 calcium nitrite ratio. But that's not always true actually for the nitrate. Like if I erase, oh no, that's calcium nitrate. Yikes. CaNO32. So if you actually had a common ion that was the nitrate, for every 1 calcium nitrate you put in, you get 2 nitrates out. So that's something to be careful of. But in this case, for every 1 calcium nitrate I put in, I get 1 calcium also in there. So this is like I'm really adding 0.01 of this calcium. Okay, so now let's find what equilibrium would be for that. If I add up the values, I get x plus 0.01. And over here, 2x, I didn't add any fluorine, so that's just kind of a mute issue. I get 2x here. Okay, and what the question is saying is, what's the molar solubility of calcium fluoride? So that means, like, how many moles of calcium fluoride can you add per liter that'll actually dissolve? Well, the amount of calcium fluoride you put in that dissolves is completely dependent, or a 1-to-1 ratio is a better way to say it, of the calcium ions. So for every 1 calcium ion you put in, 1 calcium fluoride has dissolved. So really what I'm trying to solve for here is how much calcium ions do I have in the solution? Or how much of the X do I have? Okay, here we go. I'm going to put them into my KSP. 1.7 times 10 to the 7th equals, calcium is X plus 0.01. My fluorine is 2X, and it's squared. Now, hopefully you can kind of see the land I'm headed down here. By the way I'm looking, I'm going down quadratic equation land, which chem gods hate doing. So I'm going to assume that x and 0.01, I'm assuming that 0.01 is much greater than x. If I do that, this simplifies down to 1.7 times 10 to the 7th equals 0.01 times 4x squared. This looks a lot nicer. So now I just got to do some math magic to solve for x. I'll assume you could be able to do that. Divide by 0.01, divide by 4, square root of both sides. I get an x equal 3.12 times 10 to the negative 5. Now that is a concentration thing, so I'm going to call it with units of molarity. That just makes sense. So now if I relook at my question, I'm supposed to calculate the molar solubility of calcium fluoride. Well, X is the 3.12 times 10 to the negative 5 molar. That's how much calcium ions I will have in here, even when I've got that 0.01 molar calcium in there. So this amount of X is how much of the calcium comes from the breaking up of this calcium fluoride. So the molar solubility of this calcium fluoride is equal to the molarity of this calcium ion. So my answer is this is 3.12 times 10 to the negative 5 molar, or molar solubility of calcium fluoride. I hope that kind of makes sense. One thing I do want to do that I kind of forgot for a second there was I did make an assumption right here, so I should kind of check my assumption. I assumed that X is much smaller than 0.01, so I would want to do 3.12 times 10 to the negative 5, that's my X value, divided by what I said it was smaller by, 0.01. If I find that as a percentage, it's a 0.3%, I'm assuming. So it's like a 0.3% error. That's a fair assumption. Anything less than 5% is always good. So that kind of checks out. So my answer is good. I hope that helped.